So when you say you did that all, then you replicate this.
Okay, any questions on the homework? Yes, John.
So last time you talked about problem 1.
Yeah.
And I remember you wrote 1,000 on the board, but I forgot what you said about that 1,000. And so I was wondering if you're considering 1,000 steps and looking at the probability at all of those steps, which would be a huge tree, or if you're saying you run a simulation one step 1,000 times. Can you just go over that again?
Sure. I had forgotten the details. Uh-oh. Do I dare bring up my web browser? I forgot what was the last thing I was looking at. Okay, not so bad. I've just learned from experience that it's terrible. It's a terrible faux pas to walk into in front of an audience, plug in your laptop, power it up without knowing what's going to be projected onto the display, which is being recorded for posterity. It's just very, very bad idea.
Yeah, so you got something only up on the screen, but you got something else. Now, what's too fun thing that up on those other screens, you just switch to or what I do is I just close everything.
But at least on Mac OS, there's the annoying feature that when you reopen the browser, it reopens by default, it opens all the windows you had open. Okay, so John, please go ahead. What was your question? So this was for problem 1?
Right there.
Yeah. Okay, so let's see. What was I saying about this? I think, well, so first, a comment about these first two problems. I think that nearly all of you will write a program to do this. Some of you will attempt to calculate it, and I'm interested in your attempts to calculate these probabilities. I think it's much harder to try to calculate the probabilities. But that said, in terms of the grading, if you attempt to calculate the probabilities, then you won't be graded on whether you have the exact right response. You'll be graded by the content of what you produce. So what am I saying? With simulation, if you write a program to do it, the program very quickly will give you specific numerical answers for these 3 conditions. That is the correct answer to the problem. If anybody succeeds in calculating those same correct values, I'll be impressed and interested because it's hard. And that's to some extent what I'm trying to, I don't know if that's what I'm trying to get at with this question, but it's one of the underlying themes of the probabilistic or the stochastic interpretation of chemical reactions. And it's almost a philosophical question. Why is it that we can pose a very simple problem in terms of the information content in the problem? It consists of this simple set of reactions. Where is it? It would be this one here, which is 2x plus 1 plus 1x2 plus 4x3. So I guess there we have 12 separate numbers. So given 12 separate numbers in this simple structure, and then a few additional numbers, the starting state, which would be 333, and the conditions, 575, there doesn't seem to be much in the way of complexity in how the problem is structured, and the answer is a specific numerical value. And so a question that I have is, why is it so difficult to simply calculate the answer? Now, those of you who have the mindset of studying physical chemical systems, you'll say, well, because what we're doing here is we're specifying there's a set of chemical reactions, and the reactions will fire many times before the conditions are met, and the complexity is simply that you have to track what's going on physically. Maybe, but I'll be interested if anybody has... Yeah, go ahead, John. I'm babbling.
So I guess my question is, maybe I just don't understand it.
Yeah, I haven't started to answer your question. I was just babbling. Okay, let me stop babbling and answer your question. So here is the straightforward way to solve this problem. Actually, I shouldn't tell you guys everything you need to know. But the straightforward way to solve this is you assume you're told that you start, I think I say 333. So 3 molecules, 357, sorry. (357). Now, there are 3 possible rules that can fire. So you can go here, go here, you can go here. Let's just... So you can have... So this will be x1, x2, x3. You can have 2 less of x1, so you can go to 2. You can have 1 less of x2 to 4, and then you can have 4 more of x3, so 11. Thank you. So you can go from 357 to 1411 if reaction R1 fires. And if reaction R2 fires, you'll go somewhere. Reaction R3 fires. And then from here, 3 reactions can fire. Or perhaps not 3, because here you might have hit the limit that you just don't have enough molecules of X1 for R1 to fire. So already you're starting to prune the tree a little bit. But this tree, or I guess it's a tree if we look at it upside down, this tree is growing, growing down on the board. And the question is, if we were to examine the entirety of this tree, how often, or what is the probability, that we hit any one of these conditions, whereas I emphasized last time, each one of these conditions is a terminating condition. So as the tree grows, if it hits a condition where x1 is greater than 5, so let's say over here we hit a condition 5, 4, 2. Then this is a terminating condition. The tree doesn't grow any further. We assume that things stop right there. So that's one eventuality. So that's one condition. And then there's the other 2 conditions, x2 greater than or equal to 7, x3 less than 5. And what I want you to do is to estimate or compute the probability of hitting any one of those. So now, what's your question, John?
I guess that answers my question.
But rephrase it or restate it.
The way I understood it was that, so obviously with the 1, 4, 11, you can only go with 2 more reactions. But still that tree could grow infinitely.
It could.
And that you would want to know, like, and that's where my question arose.
Yeah.
Since I think it could go infinitely, but maybe not.
Yeah, I don't think this one does grow infinitely.
Okay, I just haven't tried it yet.
Yeah. Meaning that if you write a program to simulate this, so what I was saying last time in terms of the number 1,000, that was your question. The straightforward way to do this, I think most of you see this, is just run random trials, the so-called Monte Carlo method. So set up a program where you start at 357, pick the reactions at random according to the probability distribution, and do so until you hit a terminating condition. And assume you have 3 buckets. The bucket condition 1, the bucket condition 2, the bucket condition 3. Start your simulation. Do it until you hit one terminating condition. If you hit here, this was the terminating condition C1, drop a marble into the bucket C1. Do another trial. Maybe you again hit C1, then C2. Continue to populate these buckets until you've done this 1,000 times. Then estimate the probability as the number of marbles divided by the total number of marbles. So very straightforward.
Right. I was thinking, say you chose reaction 1, you would still have to analyze what reaction 2 and 3 would end up doing and get the probability of all of those nodes of the tree.
Well, so the thing is, you do, at each step, have to calculate the probabilities, because the probabilities change depending upon the state you're in.
Right.
So you're always recalculating probabilities.
I know, but I meant you have to calculate all paths.
Well, so this is the intriguing part. So somebody who wanted to calculate this as opposed to simulating it. What I mean by that is there's a probability value here, here, here. Probability values throughout. In principle, every terminating condition, you can compute the probability of getting to that terminating condition or getting to that node of the graph by multiplying the probabilities along the path that leads to it and adding separate paths. So it's a series of multiplications and additions. And you could also write a program that did that instead of generating a random number and making a random choice, would simply compute probabilities as you descend. And I think some people will attempt to do that. It's very difficult. Has anyone tried to do that? It's surprisingly difficult because even for this small example, the tree grows to be quite large before you hit every possible leaf where it terminates. And it's not that a program can't handle that, but the probabilities start to get very, very, very small because there'll be many separate branches that lead to C1. And you kind of run into the problem that in a computer program, by the time you reach a given node, the probability has often been rounded down to 0. And if you were real clever about this, you could, instead of using the floating point representation, go for more accuracy. So preserve this by going to a data structure where you would track this. But all of that gets very complicated. Yeah. That was your question. Yeah. Okay. Yes. Your name is Jason?
I'm Scott.
Scott. Sorry, why the chuckle? Because I'm retarded when it comes to names?
No, it's the same name every time.
At the same time, I call him Jason. It's always Scott. Scott. Okay. So you know how I'm going to remember you because you're on the Alpine ski team, and Scott makes goggles. So
Yes,
Scott goggles. Okay, got it.
I don't have a single pair of Scott equipment though.
Okay.
Anyways, so problem 2, I think there was a statement where you said you were supposed to simulate it for 5 steps.
Yeah. So problem 2 is the same setup, except here, what I want you to do is to look at the. I should call this a lattice. The lattice as it descends.
Just the first 5 layers.
Or first 10.
First 10.
So don't I say 10? Okay, no, I said there was 10 in the example, 5 steps. So you're supposed to go 5 down. 1, 2, 3, 4, 5. But again, here I'm not asking you to necessarily create the tree and calculate the probabilities. What I'm interested in is instead of terminating conditions, I want the distribution on the quantities for each molecular type as a function of the step. So you're doing the same process as you did in problem 1, except you're collecting the statistics along the way. Does it make sense?
So you want, on the XY graph, you want number of steps?
Yeah.
Probability? Or
Yeah. So again, I shouldn't tell you guys how to do it, but I guess I am already. Here's how I would do it. Do the same thing that you did for problem 1, meaning do randomized trials. Start 3, 5, 7, and just follow a path. As you follow the path, you'll have changing values for x1, x2, and x3. So let's just focus on x1. So for x1, we'll have 5 steps, 1, 2, 3, 4, 5. And so this will be step 1, 2, 4, 5. At step 0, you're always going to start at 3. At step 1, sometimes you'll still be at 3, sometimes you'll be below, sometimes you'll be above. So the more trials you run, you'll get some distribution of values that you can be at for step 1. I want you to collect the average of that and plot the average curve for each of them. And then after doing that, compute the expected value for each time step and the variance for each time step. Yeah. Make sense?
Yep.
Okay. Any other questions? Anybody looking? Yes, Alex.
Does a branch terminate when it reaches the same stopping condition?
No. So the stopping conditions, I think they apply to the first problem. Here, no stopping conditions. Always go to 5 steps. But just since I think this comes up all the time for the first problem, last time there was the question on what if you hit 2 conditions simultaneously? That can happen in a single step. So never go past a condition, but sometimes by taking a single step forward, you can satisfy 2 terminating conditions. It can also happen, I don't know if it happens for this set of reactions, but sometimes a trajectory can simply hit a dead end when no further reactions are possible, and it has satisfied none of the conditions. That can happen. So simply track those events. But what it means is that the probability of the terminating conditions for the first problem, these aren't mutually exclusive, or those probabilities don't necessarily add up to 1, because you can satisfy 2 conditions with a single step sometimes. And you can also have some trajectories that cannot go forward. So the probability the probabilities won't necessarily add up to 1. Okay, yes. Your name is Paul.
This problem that you have up there reads as if you only want the mean and the variance after 5 steps. But are you in fact telling us that you want it for every step along the way?
I think that's how I had it originally, but I've simplified it. So actually I want it after 5 steps, so only on the 5th step.
So then at the 5th step, you want the mean and the variance for the outcomes for each possible reactant.
Yes, for each molecular type, X1, X2, X3. Okay. What about... Okay. When it comes to these later ones, I gather people haven't looked at those. They're not especially difficult, but they're fun. So here for multiplication and exponentiation, use the concept of the absence indicator to chain together different operations. I don't think I ask you to do this. Actually I do. So I ask you to demonstrate that it works. And the question is, how do you demonstrate that it works? You can either make a reasoned argument, so what I say mathematically, I'm not sure what I meant by that, but make a reasoned argument as to why it's correct. But even better, since you've gone through the effort, many of you, for problem 1, to write code that simulates a set of chemical reactions, use your own code to simulate a set of chemical reactions to simulate your constructs here. By simulating it, meaning set of reactions, choose some set of initial values, and show that it performs the required operation of a logarithm or multiplication or exponentiation. Start from a given set of values for your different types, and show that when it runs, and it should perhaps reach an equilibrium, the equilibrium will be the correct value, the output value of Z. But I'm not expecting you guys to do extensive code development here. Don't spend time, unless you want to, developing complicated software packaged with an interface. Use your time efficiently for this. Okay. And then let me know if you have any questions regarding the switching problems. I think the setup should be quite clear. By intent, getting to the exact values that I specify for the minimum number of switches is simply tricky. And I don't have suggestions as to how you guys should solve it. Those of you who have taken courses in logic design, you may think you have an advantage. John was saying use standard techniques. They don't really buy you very much here. It's basically ingenuity playing around with the switches. Okay, let's get started. So, as I was describing last time, I was attempting to set up, how far did I get? Not very far. I was setting the stage for the following conceptual problem. how do you decide whether two circuits compute the exact same function? Something's growling. What was growling? Any thoughts on this? So, Paul, any thoughts on this? How would you go about doing this? The premise here is that, so the straightforward way of doing this, if the year was 1965 and you had tiny little digital circuits, would be, well, you really want to prove that these two circuits compute the same function. We're talking about functions of 0 and 1 variables here. Try it. So for every possible 0 or 1 input combination, evaluate what this circuit computes. For those same input combinations, evaluate what this one computes. This would be assembling a truth table, so writing down all possible 0, 1 values, and then show that the truth tables are identical, straightforward. But there's a combinatorial explosion here. Since we have 2 to the power n possible input combinations, that value grows very quickly to the point that for even modestly sized circuits, that won't be feasible. So I'm going somewhere with this. I won't be talking about the specifics of logic verification, but rather how can we use graphs and a graph-based technique. But just I'm going to try to prod you in terms of your intuition here. So if you were to try to characterize what is the input, the size of the input set to the problem, and what is the answer? What kind of mapping is being performed? Yeah, go ahead. Yeah, or 2n to 1. So I think the font is messed up here. But what we're going for is from 2 to the m, a huge number of possibilities, a large number of possibilities. But we're going to simply a yes or no answer. And that's going to be the critical feature of this problem, that the input size is very, very large, many, many input possibilities to consider. And the two circuits being identical, it means that they have to be identical for every one of those input combinations. But the final answer is simply a yes or a no. And so problems of that nature often lend themselves to interesting and very elegant computer science solutions. Or I shouldn't even phrase that, because this is really the contribution of circuit designers, not computer scientists. Using this graph-based technique, we can answer these questions surprisingly well. Okay, so Jack, just what is the conceptual trick? And it won't even buy us anything. But what can we do to recast this problem in a different light?
So if you model it as a binary tree with each node as a variable and the vertices as a value that variable can
But
add.
sorry to interrupt, but even before we do that, I want to know whether these two circuits are identical. How do I reformulate the problem this is a very simple question. Are they identical or not? But how do I reformulate it into an even simpler question?
For same input, they should give same output.
Pardon me?
For the same input, they should give the same output.
Correct. But so what I'm going to do is going to seem trivial, but you'll see in a moment that it'll help us a lot. What's an even simpler question we can ask than that?
They have the same number of inputs.
That's a prerequisite. If they don't, then you're doomed. Anyone? So, Jordan, do you remember what I did in 2301?
Didn't we talk about hooking both
exactly.
circuits up to an XOR,
Yeah.
to input XOR gate?
Okay.
Or I guess XNOR, whatever you prefer.
Let's go for exclusive OR. Okay, let's remind ourselves, what is the exclusive OR operation, Jordan?
It is high if there's only 1, 1. So it'll be 0, 0, 0.
So if we get 0, 0, we get 0.
0, 1, we get 1. 1, 0, we get 1. And and then 1, 1 is 0.
Let me do it so that I'm not erasing them before people had a chance to absorb it. So 0 and 1 gives us 1. 1 and 0 gives us 1. 1 and 1 gives us 0. So stated differently, the exclusive OR operation returns the value of 1 if the two inputs are different. And different is the word that we're looking for here, because the two circuits are identical if they always produce the same outputs. So someone else, how about Alex? For this circuit, I haven't done anything interesting. I took circuit A, which the Intel was using, circuit B, which I've designed, laid those two out circuits side by side, hooked up the outputs to an exclusive OR gate. But now the question of whether these two circuits compute the same function has been changed to what question?
What is the output from the XOR gate?
Or is the output from the XOR gate ... Is it ever a 1? So what I'm interested now is, suppose I hook up the circuit. I'm interested, will I ever get a 1 here? If I just keep running this, putting in values here, if I ever get a 1 that flashes up, I toss my entire construct. Yeah, Alex?
Didn't we say last time that some of these chips are so prohibitively large that you can't simulate all the input?
Correct. So I'm not suggesting I have more to say than just this. There's more to come in this lecture. So you're right. And what I've done here doesn't help. If this was our scheme, this might help us a little bit because we wouldn't have to compare the outputs, but that's all we're doing here. We're comparing the outputs. But this is actually going to be very important because what we're going to do is now construct a data structure. The data structure is going to be conceptually just a data structure that represents the function implemented by this larger circuit. It's going to be a data structure. What do I mean by that? Well, we're going to talk about how with a computer program you can someone tell us, what is a data structure? I'm attempting to define a data structure. Can someone give a definition? So John, what is a data structure?
It's a way to hold data, but you can define different types, abstract methods on those types.
Yeah, I was stumbling just as hard as you to give a definition. But from a computer science perspective, people who study the field of computer science, a long time ago, Nicholas Wirth, the inventor of the Pascal programming language, he defined computer science as two components, as algorithms plus data structures. So the data structure is you're trying to answer questions of some kind based upon data. And the data, you can store it in memory, but you can store it in memory just as a huge list. You can store it as numerical values organized in a matrix. You can store the data in many different ways. So much of computer science is discussing good ways of organizing the data. It can be a list, it can be a matrix, it can be a vector, or you can have linked lists, so you can store your data such that from each memory location you store data and you point to another memory location, so you can have lists that traverse. So the data structure, the concept of data structures is the entire concept of how you organize data such that you can operate on it. And what we'll be discussing is a data structure that represents something. And what it will represent is the function that a circuit computes. And that's in itself not so intuitive, but think of a truth table. So a truth table would also be a data structure. And the truth table here would be, if I had x1, x2, xn, the truth table would be in memory. I would have a huge list where I would start with the all zeros. I would go to 1. I would go to 1, 0, and I would go all the way down to 1, 1, 1. So 2 to the n rows. If I called this F, and I called this G, and I called this H, then the data structure for these 3 circuits, this would be this circuit, and this circuit. The circuit H would be tying together these 2 circuits. I would have F, G, H, 3 columns. Here there would be some function. Here there would be some function, say differs here, and here would be the function h. So the truth table, if I were to organize these values in memory, would be a way of representing the functions that these circuits compute. And in a truth table representation, the reason why it may be helpful to organize it this way with a function h that is the exclusive OR of these two functions is now I'm looking, the yes-no question on whether these two circuits are identical is just a question of whether in this column, anywhere, there's a single 1 or more than one 1. If there is, then the two functions are not identical. All right. So you'll see in a moment, I'm going to show you a data structure that has the feature that it's very easy to decide if the function that it represents is ever anything other than 0. What might be an important feature of such a data structure? This may be too vague of a question. Okay, let me begin to explain what the data structure is. And to tie this in with the topic of the course, in a moment I'll show you. So think of the problems that you're attempting to answer in the first problem of the homework. So in the first problem of the homework, you've got a complicated, as I tried to argue, perhaps not so complicated, set of reactions with complicated dynamics. But the question that you're attempting to answer may have a yes-no type of character to it. In problem 1, I'm asking you to compute what is the probability of hitting condition C1. But you could imagine that the question might be different. It might be, is the probability of hitting condition C1 greater than 50%? And that's a yes-no question. And so as I begin to explain to you this graphical data structure, graph-based data structure for digital circuits, think of how it might apply to the case of chemical reactions and chemical dynamics, where you have a very large input space, as it were. The very large input space is all the different integer assignments that you can make to the different molecular types, 2, 4, 7, 3, 5, 6. That set is very large. But the answer is a simple yes-no question. So the challenge, and I'll speak to you a little bit about the challenge, is how can we use such a graph-based data structure to represent the system? But first, let's talk about this, the graph-based data structures for just ordinary Boolean functions. Okay. Here is an example of a truth table, and I went through this last time, but again, to emphasize that the size of the truth table grows exponentially with the number of variables. Quickly, what is the reason for that? So, Chopin, what is the reason for that? So if you had to explain this formula here, that if we have m variables, we have 2 to the m rows, how would you explain it in words?
Each variable can be 0 or 1. So,
Perfect.
So for each combination of a variable, all the other combination of the other variables have to be taken.
Perfect. So if we have, for a type x1, we have 2 combinations. It can be 0 or 1. That's 2. For x2, we have 2 combinations, and it's 2 times 2. Times 2 times 2. How many times do we multiply by 2? Well, m times, so we have 2 to the m possibilities. I'm just making sure everybody's on the same page as to why, if you have 2 possibilities and they're multiplicative, the number of possibilities, you get this exponential blow-up. So here is an alternate representation. It's going to be a graph-based representation. And our goal will be to represent this truth table as a graph. I'm not showing you. I'm going to build up the format as I explain it to you. This truth table, we all agree how to interpret it. Each row tells us a possible assignment of zeros and ones to the variables, x1, x2, and x3. And the final column tells us the value of the function for that assignment. So instead here, let's organize this exact same information, but in the form of a graph. Quickly, I think I babbled about this a bit in class, but to make sure we're on the same page, who's sitting next to John? Who's your name? I can't remember. Stephen. How can I remember that?
I don't know.
Stephen. Trying to think of a mnemonic that somehow is going to be associated with your appearance that will help me remember Stephen. Coming up with nothing. Are you physical? Do you resemble a famous Stephen?
Stephen Hawking? I hope not. I don't know.
I don't see much there. You have a nice round face. He doesn't have a round face. No, I don't see much there. Yeah. Okay, we'll work on that. Stephen. So I've forgotten what I was going to say. What I was going to ask. So what is a graph in a mathematical sense?
A series of nodes where you have edges connecting these different nodes.
Yeah. So if you pick up a paper that is published by a mathematician that uses graph theory, it always begins with the famous statement. Let G equal a collection of vertices and a collection of edges. So the graph is a collection of vertices. We can call them vertices, we can call them points. Mathematicians usually call them vertices. Computer scientists often call them nodes. Vertices, nodes, points, all synonymous. What is a vertex? What is a node? What is a point? It's an abstract concept. It doesn't, you may think it's a coordinate, but it doesn't necessarily have a coordinate to it. It is just what it is. It is just a basic entity. Edges are connections between vertices. So one feature of each vertex is, I guess, it has to be named, or we have to agree what is a given vertex. So the vertices may all have names. They may be A, B, C, D, E, F, G, and H. And edges are going to be pairs of vertices. So we may have an edge between B and E. We may have an edge between C and D. This may be our graph, a collection of vertices and a collection of connections between the vertices. So very simple, basic concept. But based upon that concept, people can do interesting things. They can solve interesting real-world problems. A famous example is the traveling salesman's problem. So, Stephen, what is the traveling salesman problem?
So isn't it where you want to minimize the walking distance of the
Yeah.
salesman?
Who has
you
to
want to hit every single node.
Yeah. So imagine that the vertices are now major cities in the US. And so I guess here each vertex does, well, to set up the problem, you start with a map of the major cities of the US, and you map out the distance pairwise between each pair of cities. So between Minneapolis and Chicago, there's one distance. There's also one distance between Minneapolis and Dallas, but there's also a distance between Chicago and Dallas. So between every pair of cities, there's a distance. The traveling salesman's problem is you have to create an itinerary that starts in one city, let's say New York, and visits every city in the country and ends up in Los Angeles. And the question is, you want to do so with the least amount of traveling. It's a famous problem. It's famous for a number of reasons. But it's often given as the prototypical example of an NP-complete problem. It's not, in a sense, the most basic NP-complete problem that you could come up with. I won't talk about NP-completeness, but NP-completeness is a very important concept in computer science. It is a meaningful measure of the complexity of the problem. And the traveling salesman problem is a hard problem, meaning that nobody can come up with an efficient algorithm that will solve the traveling salesman problem. All right. So, but that's an example of how a graph I don't know if this is a useful problem, but and the theory of how we analyze graphs can be useful. Here we're going to use graphs in a more specific way. We're going to use a graph to represent a function. So how am I going to do this? Jack, this is what you started explaining a moment ago.
Yeah. So, yeah, if you set it up like a tree, then each variable has two possible outcomes, and each of those leads to the next variable, which also has two. So it's just kind of exponentially getting bigger until you get to the final result.
Perfect. So it's beginning to look like the trees that you were looking at in problem 1. You can begin to see the connection here. But here we're just talking about 0 or 1 variables, x1, x2, and x3. And the graph is basically listing all possible values for the variable. So, but first to explain, the metaphor that I like, sometimes I get way too chatty in class, but has anyone been to Japan? And did I talk to you about this in 2301? Have you played pachinko in Japan?
I did not play pachinko, but
You know what pachinko is?
yeah.
So if you travel throughout Japan, especially in the suburbs, you'll see what look to be like amusement arcades, but they're neon signs lit up. And they're all over the place. And you walk into one of these places, and instead of video games, it's all the same category of game. They're called pachinko games. The pachinko games, to me, they look extremely boring. It's just a set of vertical pegs, and you have a little nozzle you control the direction of, or sometimes you don't even control the direction of it. And it's shooting out little silver marbles. The marbles, they shoot out, and then they bounce between the pegs, and they land in holes. But it's like a continuous fountain or a stream of these marbles that come out. And depending upon which holes they land in, lights flash, and sometimes you win, and sometimes you don't. If you win, then you get more marbles. And so you start by walking up to the pachinko machine with a little bag of marbles. You pour it in, it shoots them, and sometimes you win more marbles, or sometimes you don't. And you look at this and you say, okay, maybe a 5-year-old would be amused this for the while, but you have adults sitting there playing this, and I was puzzled by it. But even more puzzling is that sometimes you notice that there's a weird lineup of people in the alley next to the pachinko parlor. So Jack, can you guess what's going on?
No.
Gambling's illegal in Japan, like in many countries. But like in many countries, it's condoned. And pachinko is a form of gambling. So what you do is you can take your little bag of marbles at the end, go around to the side of the pachinko parlor, and exchange your bag of marbles for money if you've won. And even that's cumbersome because people don't like to carry around bags of marbles. So instead, you can win something like a stupid stuffed animal, and then you can take the different stuffed animals, have different amounts of currency. So it's an organized form of gambling. And it's weird. All right, so where am I going with this? Here, I like to see this as a game of pachinko. So imagine that you drop a marble in the top. Then, depending when it hits the variable x1, if the variable x1 is 0, the marble goes, which way are you facing? It goes left. If the value of the variable is 1, it goes right. So the marble follows a given direction. The marble follows a direction until it lands in a given bucket at the bottom. The buckets are labeled with values of 0 and 1. So depending upon the label of the bucket, you determine the value of the function. So does everybody see how this graph now represents a Boolean function? Depending upon the assignments of the variables, every marble that you drop will land in a specific bucket. And if that bucket evaluates to 0, that means the row of the truth table is 0. If it lands in a bucket labeled 1, it means that the marble has landed in a bucket labeled 1. Okay. But this is a graph now that represents the truth table. But for the time being, this has no apparent advantage. So Alex, why does this have no apparent advantage over the truth table?
Well, still just as big.
It's just as big. Perfect. Why is it just as big?
You still got the same number of outputs. You look at each input individually.
Yeah. Okay, good. But that's exactly right. Exactly the answer I was looking for. Here, this is what's called a complete binary tree. It's called a complete binary tree because you split things, you split things, you split things, always by 2. How many nodes are there in a complete binary tree as a function of the number of variables? Does anybody know this? So here we have...
So the I times 2 to the n minus 1 or something
Exactly. So let's simplify the question. How many buckets are there at the bottom if we have m variables? 2 to the m. So in a binary tree, so how many nodes are there above it? So the answer that you probably vaguely remember is there are nearly as many nodes, in fact, as many nodes minus 1, above the last row as there are in the last row. So the last row will contain 2 to the m nodes, and the sum of the total number of rows above it will be 2 to the m minus 1. We have 7 rows above it. We have 7 nodes above it. We have 8 nodes in the bottom row. So this has often been used as the argument, so you probably heard this, that there are more people alive today than there are people who have lived and died since the beginning of the evolution of our species. And that argument is actually wrong. It's wrong because our human lineage is not a binary tree. You say, well, it has to be. Each person has exactly 2 parents. But the problem is you don't have to go back very far between, and I've actually done this with my own tree, where on your mother and your father's side, the trees meet, just because people tended to live in small geographic locations. Anyways, okay. So, good. Quickly, Alex, how do we construct this tree? Meaning, the part of the tree for m variables, the structure of the tree seems given. But this bottom row is where I specify the information. How do I decide upon the zeros and ones that go here?
Just follow the path down the tree, right? Aside from looking at your truth table?
Well, no. Suppose you can look at your truth table.
Well, you have a path where you specify what each of your decision variables were along that path. So you can say, okay, well,
Yeah, that's true.
I decided 0, 0, 0 here. Oh, what's my function evaluation
Perfect.
with that? Oh, it's 0.
Perfect. That's exactly right. But can anyone look at this column of the truth table and this row at the bottom and immediately notice something? They're the same. I've just turned my head sideways. The reason for that is that to get to this particular bucket, I follow the 0, 0, 0 path, which is the 0, 0 path. To get to this next bucket, I follow the 0, 0, 1 path, which is 0, 0, 1. So you'll notice that the way that I've laid out the truth table in terms of toggling the values between 0 and 1 is, in a sense, exactly the way that I would organize paths going from the source to buckets in an organized fashion. Does everybody see that? Okay. All right, let's move on. But as Alex pointed out, I've wasted your time. I've wasted a lot of your time in this course. But I've wasted your time because the graph is just as big as the truth table. So what's the advantage? Yes, John?
Does it have something to do with the height of the tree being the logarithmic of the number of variables?
Not so much that, but, and those of you who heard this story before, you know what's coming next. But what can I do to this graph? I can come up with a smaller graph. So what would you do? Just
Find paths that are the same trajectory.
Yeah.
Given.
But where would you start with this graph specifically? How would you make this graph simpler? This one on the board.
Just start with the bottom row.
Perfect.
All the zeros, combine all the zeros.
Very good. So what we can do is combine all the zeros, combine all the ones. Why do we need 8 different 0 buckets and 3 different 1 buckets? So everybody understand what I did? Just take the buckets, slide them one on top of the other. So that makes it simpler. But now is going to be a set of tricks, and I'll explain to you systematically how you do it. But we can continue to make this graph smaller. It's called compacting the graph. So what can we do next, Jesse?
You move to the next level up
Eh.
and do the same thing.
But specifically, what are you looking for as you move at a level up? Combining the 0 buckets into a single bucket and combining the 1 buckets into a single bucket, that's simple and intuitive. But beyond that, what are the conditions that you look for to be able to simplify the graph?
Similar to how when we did the chemical reactions and we combined trajectories, you would do the same thing if like 2 things which evaluated to 1 gave you the same output, and 2 things that evaluated to 0 gave you the same.
Yeah. So, very good. So the first thing to notice is, I wish I had better animation, but like the optometrist, look at slide A, and now look at slide B. Look at slide A, look at slide B. So here, the fact that I've labeled what appears to be a single edge with both 0 and 1, it means that I've combined two 0 buckets, which means that now the two edges are on top of each other. But two edges on top of each other means that we have an opportunity for simplification. Why? Because this node, x3, is now irrelevant. It's irrelevant because when we come to x3, we're always heading to that bucket no matter what. So let's just get rid of that node. So just erase that particular node. So we erase that particular node, and here we are. So that's one opportunity for simplification that, imagine if you're writing a computer program, it's obvious. Whenever you have both outgoing edges from a node going to the same place, eliminate that node. Everybody understands what I did. I took the outgoing edge from the node above it, and I redirected it to where I redirected the incoming edge from the node that it came from to the place where both outgoing edges were directed. Okay, what next, Jesse? What other simplification can I do now? I don't have overlapping edges, but there's still an opportunity here. Someone who hasn't seen it before, otherwise it's no fun. Yeah, Paul.
Can you combine the center too? Because
why?
The 0 in both cases goes to the 0 and the 1 in both cases.
Very, very good. So here, suppose that using the pachinko analogy, I dropped a marble and it landed in this particular, or it hit this particular pin. Based upon the value of x3, it's going to go to 1. x3 being 1, it's going to go to 1. x3 being 0, it's going to go to 0. It means that what happens next is a function of x3, is what I described. But suppose that the marble instead hits this pin. I'm again looking at x3, and what I decide to do next is exactly the same. If x3 is 0, I go here. If x3 is 1, I go here. So playing the optometrist game, and in fact, I can also do the same for this x3, can't I? So this particular x3 does, because this one, so in the ones and the zeros, this 1 means it applies to this edge. Dotted edges are 0, solid edges are 1. But all three x3s lead to the same outcome if I land there. So what I can do is, and again, pay attention, x3, I'm going to slide every x3 on top of every other x3. So take each x3 node and slide them on top of each other. If I've done that, now I have a single node x3. Did everybody follow that? So that was a simplification. All right, but now what can I do, Jesse?
Now one of your x2s.
Now one of the x2s can go. So it's just a successive set of simplifications like this. Now a point to notice is that these simplifications, and you anticipated this, Jesse, is the simplifications start from the bottom and they go up. Meaning, initially we've got a complete binary tree. By combining the buckets at the bottom, we can then combine some of the nodes above. Combining those nodes above, we can combine nodes above that and above that and above that. And indeed, yeah, John?
I have a question.
Yeah.
So to make this tree, you have to have the truth table. But I thought the problem was that...
I'll talk about that. That's, again, an excellent observation. In fact, we don't need the truth table to build this structure.
Okay.
So this is a way to explain what's going on. But we can build up this data structure directly from the circuit without ever going to the truth table. While I'm babbling, think about how we might do that. Okay. But an observation here is, for this data structure, it will tend to look like a middle-aged American. What does a middle-aged American look? I'm Canadian, so I can rag on Americans. They've got they've got small shoulders, they've got small legs, and they're round at the middle. And so it means that the top is going to be narrow, the bottom is going to be narrow, but the further we go away from the bottom, the fewer opportunities we have for simplification. That's going to be the typical structure here. But nonetheless, this representation, it's actually no longer the dominant representation in the field of logic synthesis. There are even better methods than this that have since taken over. But about 15 or 20 years ago, it was really revolutionary. It really enabled, even more than 15 or 20 years ago, the modern computers that we would have could not have been built without people making this observation, because go back 30 or 40 years, and people really were writing down truth tables in order to describe circuits, and they were verifying circuits by going through truth tables. But with these types of graphical data structures, you can very easily represent functions of 10,000 variables. So imagine a truth table that would be 2 to the power 10,000, inconceivable, but the graphs are manageable in size because of this compaction. And as I'll describe in a moment, and John anticipated this question, it's not only the fact that we can represent the function in a compact way, but we can also build this representation efficiently, and more importantly, use this representation. But that'll lead to my first interesting question, which is, let's go back to the original question of you as the Intel engineer. If you had to answer the question, are circuits A and B identical? Now, specifically, what would you do if you had access to the binary decision? By the way, this is called a binary decision diagram. I'd call it, well, a decision diagram, think of a flow chart in the company, yes, no type of decisions, and then you arrive at a 0-1 answer. So it's a decision diagram or a binary decision diagram. But John, if you had access to the binary decision diagram, if you could build the binary decision diagram that represents a large circuit, how would you use that to try to answer the question of whether circuits A and B were identical? There's something that I haven't told you about binary decision diagrams that's going to be a critical feature. So where am I going with this?
Just a single line to 0.
A single input variable to 0?
No, the graph for H should optimally be just one path.
That's very, very good. So I'm impressed. So let's say for H, which is the circuit consisting of these two circuits tied together, if I build the binary decision diagram for H, if I build it, if I get some fat American graph, then the answer is B is not equal to A. If I get, for H, a single stupid graph that just consists of an arrow pointing to a single 0 bucket, then my two circuits are identical. Do people see that? But what does that rely upon? There's an assumption here for this to happen. What is that assumption? Yeah, Scott.
So I have a question that might be this assumption.
Yeah.
Does this graph always collapse to the variable to only 1x3, 1x2, 1x1?
No, it can collapse even more than that. You can eliminate variables altogether.
But can there ever be 2 of the same variable?
That's 2 of the same variable. Yes, there can. I thought you were getting at exactly the point. So Mackenzie?
I think that in the reduced form, it's unique.
It's unique. This is the critical point. That suppose that there were, after doing all the full collapsing, there were different ways of representing the same function. And based upon what I've told you so far, your intuition might be sure there might be many different ways. Why? Because I haven't told you a systematic way to go about doing the collapsing. We said, oh, look, we can collapse x2. Oh, look, we can collapse x3. Oh, look, we can collapse x2. But you might say to yourself, well, suppose I decided to collapse this node first and then this node. Perhaps you'd arrive at one structure, and there'd be no further collapsing possible. If you tried a different ordering, perhaps you'd arrive at one structure where there'd be no further collapsing possible. Those might be different structures. They still represent the same function. So in other words, what's the guarantee that if you do the collapsing? Obviously, if the function h is always 0, this is a valid representation. But how do you know that you arrive at this representation? So John, ideas? Or what I'm asking, in other words, is why is this representation unique? Computer scientists use a dumb term. They call it canonical. Have you guys ever heard this? No. If you look up the dictionary definition of this, it's weird. It relates to canons of the church. And so outside of computer science circles, canonical, what do you mean by that? But in computer science circles, what canonical means is there is a unique way to represent this according to the convention that you use to represent it, which sounds like a circular definition, but it means that here the representation is canonical if we decide upon an ordering of the variables. So if we decide upon an ordering x1, x2, x3, then there's only one way to represent the collapse circuit. Okay, but I'm perhaps prodding you guys too hard today, but can anyone anticipate what comes next, which is going to be my proof or my argument as to why the representation is unique? Factor, go ahead. Uh-huh. And if you can use to factor it, there's a... where are you going? Yeah. No, it's good. So Mackenzie, how would you prove that it's unique?
I don't know how to do like an official proof, but like no matter which path you follow, I guess, like, or no matter which order you follow the paths, like you're still going to get the same answer.
Mm-hmm. Yeah. But here, I guess, what we have to argue is that no matter in what order we do the collapsing of the nodes, we always can perform the same ultimate set of collapsing, right? So the argument has to be that if we perform some sort of collapsing, like, where are we here? Here, if we eliminate this particular x3, it doesn't preclude us from doing further collapsing. And that's not at all obvious if you begin to think about it. So Jordan, ideas?
Is it because like the most simplified version, simplified form of a function is in itself unique?
I don't see that, because the fact that there's, in other words, to use a bit of jargon, why can't you get stuck in a local minima? You know, in optimization techniques where, let's say, you're doing, you want to find the lowest point on a hill. If your argument is simply always go downhill, then you can go downhill and get stuck here, whereas only if you went uphill could you arrive at the true lowest point. So it's not at all obvious, or it wasn't obvious to me, why this should be the case, that it's unique. But I'll attempt to show you a proof. But any further ideas? I'm just trying to prod the intuition. So Chopin, how would you argue that this is unique? What's your intuition? No idea? Okay, good. Anyone? What's your name behind Stephen?
Jared.
Jared. I'll try to remember that. Okay. Is that what comes next here? Okay. I'll step through this. I promise you this proof that I'm going to give you won't be satisfying, as proofs aren't, because I'll simply make the argument a series of statements, and you'll have to disagree with one of the statements I make in order to disagree with my final claim. And this can be annoying. But in the end, such proofs are the best and only way to understand sometimes an explanation of something that's not intuitive. All right. So here the statement is that it doesn't matter in what order we perform the eliminate and merge operations. So the eliminate operation is when we eliminate a variable because both of its outgoing edges go to the same place. The merge operation is when we slide two nodes one on top of the other because both of their outgoing variables go to the same place. Outgoing edges. All right, so we're going to use induction. So what is induction? What is proof by induction, John?
You prove like a base case, and then you add one more step, some step, and you just basically prove that step based on your base case or something.
Yeah, good. Anyone else? You missed kind of a little bit in your answer there. Yeah.
You prove the base case, then you assume it's true for n.
Yeah.
And then prove it's true for n plus 1.
Yeah.
And then it's true for n equals 2, n equals 3.
Then it's true for all values of n.
Yeah.
It's one of these proof techniques that you'll encounter often when you read papers. And if you're never taught the basics of it, it kind of seems intuitive, but not quite. Here's how my father described it, and this is a good metaphor. Imagine that there's a row of boxes that extends from U out to infinity. Each box is locked. But inside each box, there's a key that, if you could open that locked box, would open the next box, right? So, bunch of boxes, inside each box a key, each box is locked. The key that's inside the locked box always opens up the next box. So initially, all the boxes are locked. You got nothing. But if somebody gives you the very first key, then the very first key allows you to open one box that gives you the next key, and then all boxes are open. So in proofs by induction, usually, often the base case is very simply to argue. You can argue that what you're trying to prove is true if you have some very small problem size. Let's say you have a tiny graph. It's true. The hard part to prove is the inductive step, which is what Scott described. The inductive step is you have to somehow formulate your problem so that you assume that you've opened every box up until the current box. And you have to prove that if you can open, that if every box is opened up until the current box, that in fact there is a key. So you have to prove the presence of the key inside each box that opens the next box. But you have to do it for any box that you choose. And this is the hard part. So it means that you have to assume that it's true, let's say, in this case, we'll do it on the number of variables. We want to prove that the binary decision diagram is unique. There's only one way to represent it for any number of variables. So we're going to show that this is true if we have one variable. And then we're going to show that suppose that it is true for any decision diagram that represents up to m minus 1 variables. Then we have to prove that it is true for m variables. That's hard, because you have to argue in terms of a general m and a general m minus 1. But if you can do that, then you've proved it for all cases. Okay, so where am I going with this, Alex? You look a bit tired. I'll try to wake you up. It's not going to wake you up? So, okay, Jack.
I'm still going to answer your question, but it's not going to make me less tired.
Okay, so but just inductive step. What would be inductive step here? So base case we agree upon, I've actually done this for 0 variables. For 0 variables, there's only one way to represent the function. It's either 0 or 1. You just have a bucket and an arrow that points to the bucket. Now, recall what we're trying to prove for the inductive step. The inductive step is we're going to, and you always in proofs like this have to keep in mind what is the goal. The goal, I said y'all, I like that. What y'all have to keep in mind is that the goal here is to prove something. What we're trying to prove is that if you give me a binary decision diagram that's fully compacted, all the merging and eliminating done, that there's only one such diagram possible that represents the function. So it's unique. That's what we're trying to prove. Is that okay, Chopin? You're grimacing a bit.
I didn't quite catch it.
Oh, okay. So what I want to prove is there's a given function. Let's say there's a truth table. And you construct a binary decision diagram. And for the binary decision diagram, you do all the merging and compacting possible. And then eventually it ends, meaning there's no further compacting possible. The claim is that that resulting graph is unique. You couldn't have done any sequence of merging and compacting that would lead to a different final graph. And that's not at all obvious or intuitive, right? But is that clear?
But which is the one which I'm finally...
Pardon me?
So whichever way we're doing will be reaching the same graph?
Yes. Whichever way that we're doing the merging compacting gives us the same final graph. That's what we want to prove. So the inductive step here is we're going to say it's going to be on the number of variables. So we're going to start because every function that you give me has some predetermined number of variables. So if we start with 0 variables, there's only one way to do it. If we have 1 variable, again, it would be easy to show there's one way to do it. 2 variables, 3 variables, 4 variables. So a function of m minus 1 variables, we're going to assume that my statement is true. That if we have m minus 1 variables, there's only one way to represent that graph after doing all the merging and compacting. Based upon that, now we have to show that for m variables, for a function of m variables, there's only one way to represent it. So, Alex, how would you begin to set up that proof?
Well, the hint is we use an approach. But to start with...
By the way, ROBDD, that's a horrible alphabet acronym. This means reduced ordered binary decision diagram. Binary decision diagram, what that is ordered, simply means that I've decided on the order of the variables. That's important. Reduced means I've done the full compacting. Anyone else want to give a track in? Oh, we're just running out of time here. Mackenzie, do you want to give a stab at this? Where would you go to prove that? So perhaps the first observation is, how are we going to go from n minus 1 to m? So we assume that the statement is true for all functions of m minus 1 variables. And now we want to look at a function with m variables.
I mean, you have to add that extra variable
Yeah.
to know that it can only be 0 or 1.
Right. And where are we going to put that extra variable?
At the bottom?
At the top. Close. So we're going to put that extra variable at the top. So now imagine that the statement is true for all functions of m minus 1 variables, and let those m minus 1 variables be x2 to xm. The extra variable that we're adding in this case, call it x1, we'll stick it at the top. Why at the top?
So if you start with the base case of just the 0 and
Yeah.
1, then you know that's the bottom, so then you must be adding to the top each time.
Where I was going with this, why we'll put it at the top, is that in a binary decision diagram, that first variable only appears in one place. The x1 only appears in one place at the top. All other variables, we may have many x2s, many x3s. By the time we get to x64s, we may have a bazillion x64s. But the x1, if he's sitting at the top, there's only one of him. So now the reasoning for the inductive step can be performed on the resulting structure. So the reasoning, I was looking at this before lecture, and it holds together, but I hope this won't complicate things. What I'm going to say, I think in addition to a proof by induction, this is also using proof by contradiction as a proof technique. So John, quickly, what is proof by contradiction? There's also a proof technique that I like a lot. It's called...
You assume something,
Uh-huh.
and then you work from that until you arrive at a contradiction of what you first assumed.
Uh-huh. And that's it. That's all you have to do. There's also a proof technique I like a lot. It's called proof by intimidation. That's where you grab something heavy and you just say, it's true, it's true, it's true. I think that we're running out of time. Let me postpone the discussion of the proof by contradiction, but so at least I can finish this proof here. What I'm going to do is I'm going to say, look, suppose that I've got the same function, but I'm going to have suppose that I have two binary decision diagrams that represents the same function. And I'm going to suppose that they're not the same. So I've done the full reducing, but on the right-hand side, I've got f. On the left-hand side, I've got f prime. They both represent the same function, the two decision diagrams, but they're different. And then I'm going to show that that can't happen. They can't be different, in essence. That's not quite what proof by contradiction is. But the critical point here is that if I look at the diagram on the right and I look at the diagram on the left, each one has the new variable, x1, sitting on top. And what comes out of the one on the right? Well, there's a dashed line and a solid line. The dashed line goes to the portion of the decision diagram that sits underneath. But what is the portion of the diagram that sits underneath? So what is F0 here? Mackenzie.
Isn't that the one that's already been reduced?
It is, because the assumption is they're both reduced, but what is that function? It's It's the function that we're looking at with the variable x1 set to 0. If we have a function of m variables, and we take one variable, x1, and we set it to 0, we get a new function. That's a function of m minus 1 variables. So this is how we're going to invoke the inductive step. The fact is that the function that we get by looking at the portion of the decision diagram that starts right here, game of pachinko, this is where we drop the marble now. We drop the marble into a decision diagram because if we have a decision diagram and we prune the top two nodes, then we still have decision diagrams in terms of what we're holding on to. Now we have two decision diagrams, actually, the 0 case and the 1 case. Those two decision diagrams, they're both reduced ordered decision diagrams. And they now both represent functions of m minus 1 variables. They represent different functions. Because I've got the original function. If I set the variable x1 to 0, I get one function. If I set it to 1, I get another function. But I have two functions. They're both functions of m minus 1 variables. And by the inductive assumption or the inductive hypothesis, I assume that these two diagrams, there's only one way to produce those two diagrams. There's only one way to write those two diagrams. That's on the right-hand side. Here on the left-hand side, I'm doing the same. So it sounds like I'm doing nothing, and I guess I am. But what I'm doing here is I'm assuming that I have some other representation, any other representation of the ordered binary decision diagram, but one that's different from that one over there. But this one also has the property that if I snip it at the top and I hold on to the right-hand side, hold on to the left-hand side, I'm holding on to the top of decision diagrams that are both fully reduced and are decision diagrams for functions of m-1 variables. And furthermore, this function has to be the same as this function, and this function has to be the same as this function. By the induction hypothesis, this binary decision diagram has to be identical to this binary decision diagram. Why? Because I've assumed that there's only one way to write a decision diagram for m-1 variables. Similarly, this decision diagram has to be the same as this one. So I'm done, right? I'm not done. Why am I not done? Stephen.
I was just thinking of something funny.
So, please share. I like funny things.
Proof by discombobulation.
Discombobulation.
Just keep talking until people are yeah, it's true.
And people walk out of the room. Proof by babbling. That'll be my next joke. There's proof by intimidation and proof by boring people till they leave. Is that what I'm doing here?
Yeah, sorry.
Fair enough. We're almost running out of time, but...
The induction makes sense, though.
Well, but I haven't actually even begun the interesting part of the proof. But it sounds like I'm actually finished, right? Or not? Jack?
I don't know. I mean, everything you've said so far is like somewhat intuitive.
Mm-hmm.
So
the fact, to finish off the proof here, so the proof is basically, I assume that it's true for up to m-1 variables. I want to show that it's true for m variables. I've introduced the new function that has m variables that has x1. Previously it didn't. And I'm just basically arguing the respective subgraphs, this subgraph and this subgraph, by assumption have to be identical. This subgraph and this subgraph, by assumption, have to be identical. And now I'm just saying, okay, well, that means that the overall two graphs must be identical. That's not necessarily true. Or I have to argue why it's true. So why isn't that necessarily true? Anyone? Mackenzie, are you following?
Because it can be switched.
It can be switched? Well, if I had a complete binary tree, so if I was just splitting, then of course it would be true, but then the argument would hold. But I don't have a complete binary tree in the sense that after doing the merging and compacting, nodes in F1 and F0 can be common nodes. They can be shared. That's the whole point of the decision diagram, that I'm not just always splitting, sometimes I'm combining. So now it means that if I'm holding on to the tops, like I'm holding each binary decision diagram by its hair, I've got a complete decision diagram that makes sense, but it may be intertwined with the other one. So it means now that just the simple argument that this subgraph has to be identical to this subgraph doesn't prove that the overall graphs might be identical, because it could be that over here I have the same, ignore all this, ignore all that. Here, this is a counterexample that attempts to prove the case. Here, these are in fact two decision diagrams that represent the same function. And on the right-hand side, I've got the decision diagram that's rooted at x1. So this is the f0 and f1. This is the f0 prime and f1 prime. And they represent the same function. But here, the given node that's represented by x3 in this graph could map to both this node x3 and to this node x3. Because it could be that holding each decision diagram by its hair, they're messed up, but one is more intertwined than the other. So that could be a possibility that would destroy my proof. But in fact, this can't happen. Why, John?
Initially, you assume those are reduced to the lowest form?
Yeah, exactly. So the critical point to understand the proof is I've assumed that I've fully compacted the graphs. If I fully compacted the graph, if this node there's the word isomorphism. So when you're trying to prove that two graphs are identical, you say that two graphs are isomorphic if you can map each vertex to some other vertex. So here I'm mapping this vertex to this vertex, but maybe I'm also mapping this vertex to this vertex. If I'm doing that, then they're not identical graphs. They're only identical if I can pair up a specific vertex with another specific vertex. If I told you nothing about what we did with binary decision diagrams, you could say this is possible. And if you stare at this graph, it's possible. That vertex maps to this one and maps to this one. But this can't happen in our proof scenario because we assume that both graphs are fully compacted. And now, for the vertex to map to two pairs of vertices, it must mean that both those vertices define the same subgraphs. So if I'm holding these two guys by their hair, it means that they must each be the same as this guy if I'm holding him by his hair. But if these two guys are identical and I'm holding them both by their hair, then I would have merged them into one. So the proof relies upon the fact that the graphs are merged. This is another example that illustrates it the other way, that here it also goes the other way, that if I'm going from left to right, I'm holding two guys by the hair. Okay. Anyways, that's the proof. I don't know if that was effective or not, that the binary decision diagrams are unique. But this is the full power of the method, because now, how do we test if our circuit at Intel, our new circuit B is identical to our circuit A? Well, we just build the decision diagram for the function h. Building it, I'll show you next time how we build it. There's an efficient way to build these decision diagrams without looking at the truth table. We build it, and if the end result is just h points to 0, in other words, if in the process of building it, we're going to build it and we're going to be performing the merging and collapsing. If we build it and perform the merging and collapsing, and it always collapses down to the 0 node, we're done. If it ever doesn't, if ever we get stuck, we build it and it doesn't collapse to the 0 node, we know that the answer is false. It's a very powerful method, and one that I shouldn't tell you guys this, but it's such a powerful method that's known. It's not that this is an obscure result, but you kind of require specialized knowledge to know it. Folks on Wall Street, I'm guessing they don't know this kind of knowledge. Very intrigued by the idea of applying a yes-no type of analysis to what seems to be an intractably large set to arrive at an answer. There's so-called, have you heard of this, binary trading options? You can bet on whether the price of gold will go up or down. It's a new feature. It's either yes or no, and if you guess correctly, you get the full amount. It's legalized gambling on Wall Street. It's speculation, legalized gambling. But these binary variables are new, and people within circuit design know something about analyzing circuits that have tremendous number of variables that perhaps outside of circuit design people don't know. Okay, maybe I intrigued you a bit with that decision. You guys all want to get rich like me.
So the takeaway, you can go make a bunch of money on Wall Street with what we learned in this class. You're assuming every variable is binary.
I wish that was the takeaway. Yes. Then to be honest, I wouldn't be teaching this class.
Yeah. The fatal flaw in my assumption.
It's the fatal flaw of any watching infomercial and the guy's telling you how to get rich. You think about it for a moment, well, why would he be telling people? And if he can get as rich as he claims, as quickly as he claims, he certainly wouldn't be starring in an infomercial.
Unless he needs money to get rich.
Yeah, but he's telling you exactly how to get rich. So. Oh, you mean, yeah.
Like, yes, so
so his strategy to get rich is actually to create a stupid infomercial.
Yep. Unless you own the infomercial.
Yeah, that's what I mean. So.
Oh, yeah. I thought you meant like active.
Yeah, but I mean, I've met a guy who was saying stock. That's all he does. No,
He just does stock.
just stock. It's a really hard job.
Yes. I have a question on that last, your proof. So are you suggesting that if any node